Welcome to Raw Perfect classes. In this video, I will discuss about next part of theory of computation. First, again repeat what is a theory of computation. Automata theory. Theory of computation is a theoretical branch of computer science and mathematics. Means automata theory is a theoretical branch of computer science and mathematics, which mainly deals with the logic of computation with respect to simple machines, which is known as automata. It enables scientists to understand how machines compute functions, how machines solve the problems. Automata theory of computation, it enables the scientist to understand how machines calculate functions, how machines solve the problems. Its main motivation to develop such type of methods which are used to describe and analyze the dynamic behavior of discrete systems. The word automata originated from the word automation, and which is closely related to automation. Now, what is a automation? Automation is a term for technology applications where human input is minimized. It includes business process automata, IT automation, personal application, etc. What are types of automation? First type is fixed automation, programmable automation, flexible automation, integrated automation. There are some examples of automation: automata school bus, robotic gas pumps, and garage opener applications. Now, next point is automation is nothing. Automation is nothing but a machine which accepts the strings of a language over an input alphabets that is represented by sigma. There are 4 types of automata that are used in TOC. Means there are 4 types of automata machines. These are: first is finite state machine, that is also known as finite automata machine. Second is push down automata machine, PDA. Linear bounded automata machine, that is known as LBM. Turing machine, TM machine. In previous video, I have already discussed about which machine is used by which language. FA is used by regular language. Push down automata machine is used by context free language. Linear bounded automata is used by context sensitive language. Turing machine is used by recursive enumerable language. Recursive enumerable language. But finite automata machine means finite state machine is less powerful than Turing machine, because finite state machine is restrictive machine. So it is a less powerful. Turing machine is unrestricted machine which is used for unrestricted language, that is recursive or recursive enumerable language. So that's why it is more powerful as compared to finite automata machine, that is known as finite state machines. But deterministic finite automata, non-deterministic finite automata which have same power, because FA is divided in two parts, deterministic finite automata and non-deterministic finite automata. So it has same power because both converted into each other. But you should be keep in mind that NFA can easily convert into DFA, but DFA is not converted to NFA easily. So we can convert, most of all we convert NFA to DFA. Now next is a equivalence. What is equivalence? But which type of machine is equivalent to next which type of machine? First is FA is equivalent to following machines: PDA with finite stack, Turing machine with finite tape, Turing machine with unidirectional tape, Turing machine with read-only tape. This finite automata is equivalent to these machines, and PDA is equivalent, push down automata is equivalent to only FA, finite automata with stack, and Turing machine is equivalent to following: push down automata with additional stack and push down finite automata with two stacks. And next is what types of applications of different automata. For FA, design of lexical analysis of compiler is used as application. Second application, recognize the pattern by using regular expressions. This is the second application for the automata which is used finite automata machine. And third is use of Mealy and Moore machines for designing combination of sequential circuits, and it also helpful in text editors. Finite automata machine also helpful in text editors, and it also helpful and it also used for spell checkers. First, it is used for lexical analysis of compiler. Second, it is used for recognize the patterns. Third, it is used as a Moore and Mealy's machine for designing combination and sequential circuits. Third, it is also used in text editors, and it also used in checking of spelling. Now, next, second type of machine which is used for following applications in automata, that is, first is it is used in the syntax analysis phase. FA is used in lexical analysis of phase, and PDA is used in syntax analysis phase, and LBA is used in genetic programming implementation. And Turing machine which is used to solve recursively enumerable problems, and FA is used for recognize pattern by using regular expressions, and PDA is used to implement stack applications, and LBA is used to construct syntactic parse trees, and Turing machine which are used for neural networks implementation. And finite automata machine is used for designing combinational and sequential circuits by the help of Mealy or Moore's machines, and PDA used in evaluations of arithmetic expressions, while Turing machine is used for knowing the complexity of theorem, and PDA is used for solving the Tower of Hanoi problems. And Turing machine which is used for implementation of artificial intelligence. Finite automata helpful in text editors. It is used for spell checkers, and Turing machine is used in robotics applications. These are the applications in which automata is used through the finite automata, PDA, LBA and Turing machines. Now next topic is what is a DFA in TOC? DFA is a part of FA, finite automata's part. DFA means deterministic finite automata. Deterministic finite automata. It tells uniqueness of the computation. If machine reads an input string, then one symbol can read only at a one time. It has only one path input from current state to next state. In deterministic finite automata has one path input from current state to next state. It does not accept null move. It does not accept any null move. That means it cannot change the state without any input. Without any input, it cannot change state. It can contain multiple final states. It is used in lexical analysis in compiler. It is collection of defined as a 5 tuples, that is known as 5 rows. First, Q, sigma, lambda, Q naught and F. Q is used for finite set, that is related to states. Sigma is used for finite set, that is related to alphabets. Lambda is used for transition function in which Q multiply sigma, that means finite states multiply by finite alphabets, and we will find out Q, that is known as transition function. Q naught belong to Q is the start initial state, and F is related to final or accept state. Now, how to represent graphically DFA? It can be represented by digraphs, that is known as state diagrams. That is known as state diagrams. Now, what types of factors which are considered in DFA? There are first factors considered in DFA, that is the state is represented by vertices like this node. This is initial state. This is a symbol of state representation. This is the state is represented by vertices like this symbol, like Q's node. This is a initial state. The arc labeled with an input character shows the transition. If we take here this symbol and we write here A, that means this Q node state accepts the A alphabets. The start state is represented by an arrow. This arrow is show that it is a start state. The final state is represented by double circle. Double circle. This is a final state. You can send another value. Now, what is a trap state in DFA? Trap state means dead state. Trap state means dead state. In DFA, trap state will be present. First, here we start Q naught and accept A Q1 accept A from Q node, and Q1 is a final state, and it also accept itself A or B. This is a final state. Q node to Q2. This Q2 is a trap state. That state because it can't reach to final state, but it accept from Q node B. If a transition goes to a state from which it can never escape, such type of state is called trap state or dead state. Now, what types of applications of DFA? Protocol analysis, text parsing, video game character behavior, security analysis, CPU control unit, natural language processing, speech recognitions. These are the types of applications of DFA. In these applications, we use DFA. Now, this is the example of DFA. How to construct the transition table of DFA for a given diagram. We have given Q is equal to Q naught, Q1, Q2, and sigma is equal to 0 and 1. We have two transition values 0 and 1. Q naught is equal to Q naught, that is a starting state, start state, and Q2 is a final state. F represent to final state. Now, how to draw transition diagram? Start Q naught and accept 0 itself, then transition to Q1 and Q1 accept 1 from Q naught and 1 accept from itself. Then it transition to Q2. Q2 accept 0 from Q1 and 0 or 1 accept itself. Now I am going to show how to make the transition table, how to draw the transition table, how to construct. First of all, you have to take here present state, then next state for input means 0 and 1. These inputs are given in question. You can see sigma is equal to 0 and 1. That is the input. Now start from Q node. Q node. From Q node itself accept 0. So that's why we will write here Q node. And Q1 accepts 1 from Q node. So that's why Q2, Q1. So we will write here Q1. Now Q1, from Q1 to Q2 0 accept, and Q1 itself accept 1. Q2 star Q2 means final state. Star represent to final state, and Q2 itself accept 0 and itself accept 1. So that's why here we will write Q2 in 0 input and Q2 in 1 input. Now next topic is non-DFA in TOC, NFA in TOC, non-deterministic finite automata. It is easy to construct. It exists when many paths for specific input from current state to next state. In DFA, only one path. But in NFA, there are many paths for specific input from current state to next state. Each NFA can be translated into DFA. It can be defined as DFA, but two exceptions, like it contains multiple next states, it contains abselian transition. Now example is here Q node is a start state. It accepts B itself, and Q1 is the final state. It accepts from Q node A, and it itself also accepts A. On the other hand, it also accepts from Q node B. On the other side, Q2 is a state which accepts only A, but it cannot be connect with the final state. All steps will be the same as DFA for constructing NFA. And for example, here we will take an example for solving NFA. Same example here we will take. Construct transition table of NFA for a given diagram. Q node Q1 Q2 sigma 0 1. Q node is equal to Q node. This is a starting state, and F is a Q2, that is a final state. Start Q node and accept 0 itself, and then 0 comma 1, that means Q1 can accept either 0 or 1, and then Q2 is a final state. It will accept 0 from Q1, and 0 or 1 accepts itself. On the other hand, Q's node accepts from Q1 1, and Q1 also accepts from Q2 1. This is a NFA. Transition table. Start from Q node. Q node, take the input from Q node. Who will take input? Q node itself, 0 accept, and Q1 also accept 0. On the other side, Q1 also accepts 1 from Q node, and Q1 gives input to Q2, 0, and on the other side Q1 itself accept 1 from Q2, and Q2 star is a final state. 0 is accept from itself, and 1 is accept from Q1 and Q2. Now, can we convert a non-deterministic finite automata in DFA? Means, can we convert NFA into DFA? Yes, we can convert. Every DFA has an equivalent. Every NFA has an equivalent DFA. Equivalence means in the terms of language acceptance, because NFA is nothing but in which 0 or 1 or more transitions on input symbols are allowed. It can always construct finite automata which will simulate all moves of DFA on a particular input symbol in parallel form. It also gets a FA, finite automata, in which there will be exactly one transition on every input symbol. This is a note to construct DFA. When we want to construct DFA, which is equivalent to NFA, then we should keep in mind that states of DFA are a collection of states of NFA. Now, these are some steps which are taken when we convert NFA to DFA. First of all, initially we should take Q dash is equal to 5. Second, then add Q node of NFA to Q dash. Then find the transition from this start state. In Q dash, find the possible set of states for each input symbol. If this set of states is not in Q dash, then add to Q dash. In DFA, the final states will be all states which contain F final states of NFA. For example, we have given this diagram and we have to convert NFA to DFA. Here we have given Q naught which accepts 0 itself, and from it Q1 accepts 1 and itself accepts 0 or 1, and Q2 accepts 0 from Q1 and itself 0 or 1. On the other side, Q1 accepts from Q2 1. Now we will go to convert NFA to DFA. For conversion, first step is draw the transition table from the diagram. First, start Q naught 0 and 1. These are the inputs. 0 accept Q itself, so that's why Q naught. 1 is accepted by Q1 from Q naught, so that's why here Q1. Q1 accepts, Q1 gives input to itself or to Q2. On the other hand, Q1 itself accept 1 from Q2. Q2 itself accept 0 or accept 1 from, it gives 1 to Q1 and itself accept Q2. Now next step is, now we will obtain lambda dash transition for state Q naught. How to construct it? You can construct it by this method. You have to write lambda dash in round bracket. First transition from transition table, take first input, that is Q0. Q0, that means Q naught. Q naught in square, you have to write Q naught in square bracket, then comma, input is 0, and from Q2, Q naught to Q naught, so here we will write Q naught. Lambda dash square in a round bracket, in square bracket, Q naught. This Q naught is written here, this is written here, and these are written here, and this one is written here, this 0 is written here, and we will write Q1 not equal to. Then third step, the lambda dash transition for state Q1 is obtained. For this, lambda dash Q1 comma 0, that is equal to Q1 comma Q2, and again Q1 comma 1, that is equal to only Q1. Now next step in this, in next step, lambda dash Q2 comma 0, that is equal to Q2, lambda dash Q2 comma 1, that is equal to Q1 and Q2. Here Q1 and Q2, this is a new state generation. Now next fifth step, now we will obtain lambda dash transition on Q1 and Q2. Q1 comma Q2 comma 0, then we will find it by taking Q1 comma 0 union lambda Q2 0 and its value Q1 comma Q2 and Q2. Take the union. When we take union, Q1 is a common and Q1 is taken, and then Q2 is taken as a common. This is a new, this will be a transition of Q1 and Q2 from 0. Now next, in this Q1, Q2, when it accepts one input, then we take lambda Q1 comma 1 union lambda Q2 comma 1. Q1 its value and Q2's value is Q1 and Q2. You can take it, you can see it from the table, and finally union is given Q1 and Q2. Q1, Q2 is the final state as well as because it contains final state Q2. Now draw the transition table for DFA. First state is start state Q node, that is equal to Q node and Q1. Q1 is Q1 comma Q2 and here Q1. There are two states are final. First is a Q2 state final and this is a new generated final state Q1 and Q2. From Q2 and Q1 Q2 and Q1 to Q2, that is equal to Q1 and Q2, and Q1 and Q2, they both are the same. Now transition diagram. Take Q2 and it accepts 0 itself. Then draw transition Q1. That draw it accepts 1 from Q node. Then again start from it Q1. It accepts itself 1. So that's why here we draw this 1. Now Q2 star. Here we take Q2 star. It will accept itself 0. So that's why it made here Q1 comma Q2. So here we will made a new state Q1 comma Q2. From this it accepts Q1 Q2 1, and on the other side from Q1 it accepts 0 and itself accepts 0 comma 1. And here you can see this state if we not made, then also you can get result. Q2 state can be eliminated because Q2 is an unreachable state. This is a unreachable state. Now one more example. First we have given this diagram. From this diagram, first of all draw transition table. First state, this is a start state Q node. It accepts itself A or B. So here we write Q node for A, but we cannot write Q node for itself because it also accepts B. But in NFA we will not write. And here we write only Q1. Here it accepts B. Q1 accepts only B, that will be written here. But from Q1, Q2 accepts B. So Q2 is its final state, so that's why we write here star. And Q star does not give input to anybody. Neither itself accept nor it give input to anybody. So any state, so that's why it will be blank. Now first step, suppose Q dash be a new set of states of a DFA, T dash be a new transition table of DFA. So first state Q node, that is a start state. From this state we will go itself and we accept A. On the other hand, we also accept B. So in B we will add Q node. In NFA it is not written, but in DFA we will add Q node comma Q1. In third step, now we will start from Q node Q1, and in Q node Q1 itself accept A, and on the other side it will also accept B. So that's why here we will write Q node. It also accepts because it gives the Q1 value B, so that's why we write here Q1, and it also give to input to Q2. So that's why we write here Q2. In third step, in next step, now start from this Q naught, Q1, Q2. Q naught, Q1, Q2. In this Q naught itself except A. So that's why I write here. And from this Q naught, Q1, Q2, all these states except B. So that's why I write here. Now, transition table of DFA. In this, write start Q naught, Q naught, and Q naught, comma Q1. Q naught, Q1 to Q naught, Q1, Q2. Then Q naught, this is a final state because in this Q2 is present, that is the final state. So that's why it is a final state. Now we will draw this diagram. Q naught, it itself except A. Then it gives input to Q naught to Q1, B, single transition, and it also sent B to Q naught, Q1, Q2, and it also accepts itself B. On the other hand, Q naught, Q1 gives input to Q naught A. Q naught, Q1, Q2 also gives input to Q naught A. And this is a DFA conversion. This is a conversion from NFA to DFA. In this video, I have discussed how what is a automata, what is automation, and what type of application is used in automata, and what are the machines which are used in automata. That means the theory of computation, and what is a DFA, what is a NFA, and how to convert NFA to DFA. Thank you.